Hello, everybody.
Hello. Hello.
Thank you for your patience with me and missing the last class. I'm feeling better today, so I think we're ready to go to
Yay.
the next module. So let's see. We're on to the, I believe it's the fourth module. Let's and that I just made available today. There's not much there other than the class practice problems. No, making me sign in again. We're getting there. There we go. Yeah. It's titled binomial probability, but I'm going to go over in general what probability distributions are, and then what binomial probability distribution is one of those, it's a specific one. Can you understand my voice okay?
Yes.
Okay, it's a little rough. So we're going to look at probability. And they're going to look familiar because what they really are kind of like frequency distributions, but the only column they have is probability. So let me give you an example of what one of these would look like. And you'll see them drawn vertically and horizontally. So that the orientation doesn't matter. So you may have data that looks like this in a frequency distribution. And we would have some kind of data over here. And then we would have the frequency of that data. Suppose it's class grades. And the grades are possible grades are A, B, C, and D. And 3 students got an A, 5 got a B, 1 got a C, and 1 got a D. So looking at this data, and we did this last chapter, elementary probability. How would you find, looking at this data, how would you find the probability of somebody getting an A in the class?
Wouldn't you add that all up?
Yeah,
Yeah.
good job. So you add them all up. We know we got 10. Looks like we got 10 students. So what's the probability of getting an A?
3
Over
over
10.
10. 10.
very good. Always over the total number in the sample space. And the probability of getting a B in the class?
5.
Over,
10.
there we go. And you can see where I'm going with this. What are the last two probabilities?
1 over 10 and then 1 over 10 again.
Okay, very good. So that was a frequency distribution. And out to the side here, we just calculated, use that data and the frequency distribution to calculate some probabilities. So a probability distribution has the outcomes. And then simply next to that is just the probability of those outcomes occurring. And you told me that's 3 out of 10, 5 out of 10. I know 5 out of 10 would reduce, but it's a little easier to work with this way right now. Like that. Now these are called discrete probability distributions because they have a discrete number of outcomes. The numbers, remember, discrete data is data we can count, like students in a class. I can count how many students are in the class. Continuous data is data that we measure, like your height. I'd have to measure your height. I can't count your height. So this is called, in general, just a discrete one, because next module, we're going to do a continuous one. And these discrete probability distributions have a few little properties. Some you probably think are pretty trivial, pretty obvious. Every individual probability, so in a probability distribution, has to be greater than or equal to 0. And that's just because of the definition of probability. Every probability, we don't have negative probabilities. Also, every probability has to be less than or equal to 1. So we could have said, if we wanted to, said this in one statement like this. Every probability has to be between 0 and 1. Now, if I add up all the probabilities, and I'm going to use my summation sign here, the sum of all the probabilities in the distribution, what do they add up to?
10?
What was that?
Would
I think you're right. Go ahead and say what
10?
you said.
10?
Yeah, 10 over 10. So in this case, if you added up all these fractions, you would get 10 over 10, which is equal to 1. So in a probability, when you exhaust every possibility, it should add up to 1, which is 100%, because something's got to happen. So in a probability distribution, it has to account for every possible outcome. So when you add them all up, they should add up to 1 or 100% if you prefer percents. So let's look at some examples. Give you a minute to get that. All right, let's look. And I have just this another one of these practice sheets in here, which is just a old document. Well, it's an older quiz. And that's I was afraid of this. Hold on a second. I think these might all be binomial. Oh no, here we go. I was incorrect. Okay, just got to pick around. We'll eventually do all of them. All right. There we go. All right, from the properties you know now about probability distributions, can you find the missing probability? There's a probability distribution laid out horizontally. You're given 4 of the 5 probabilities. The probability for the outcome 3 is left off, but it's the only empty one. So use the information you have to fill that in.
Would it be, actually, wait, I don't know if this is right. Would it be 10 or 17? Now I'm thinking that I actually don't think that's right. Hold on.
Are you sure it's not right?
I mean, that's what I tried. I don't know. I don't know if it's right though.
If you put 10 over 17 in that spot and you add up all the probabilities, do they add up to 1?
Oh, wait, what do you mean?
I said, here, let's see. Suppose you put in this
Oh,
spot.
no, it wouldn't.
Okay. So think a little more. I think you're on the right track. You just didn't go, I think there's one more step you should have taken. Anybody, you don't even have to have the answer. You can give me what you think would be a step or what you're trying to do.
Okay, I think it's 5 over 17. Because that would equal 1.
There you go. Good job, Lexi. So if we put 5 over 17 in here, and this is where Lexi got this. We know that if we add up all these probabilities, they have to sum to 1. That's one of our properties. So let me add them up without the ones she told us. So these are the ones we were given. This is a good reason not to reduce. These fractions don't reduce, but a good reason not to reduce them ahead of time. It's a whole lot easier to add fractions when they have a common denominator. So if I add all those up, I get 12 out of 17. So then the question becomes, how much more do I need to get to 1, which would be 17 over 17?
You need 5.
Yeah, so you see how she got that? If we had another 5 over 17 in that empty spot, then it would all sum to 17 over 17, which is equal to 1. So there you go. That's how you take some, they give you enough information and you have to use a little deductive reasoning. You take the information, they don't give you the answer directly, of course, but you're like, there's some way I can use this information I'm given to find the answer. And that's how you would do it.
So the goal each time is to just make sure it's the same number over the same number,
Yeah,
pretty much.
that's a good point, Jalen. There's the goal is that it meet all 3 properties. And that's one of the properties. So you're correct. It has to equal 1. But it also can't be less than 0. And it can't, each individual property, each individual probability can't be less than 0. And each individual probability can't be greater than 1. So it's just those 3 properties.
Okay, gotcha.
And you can kind of boil them down to 2. But you're right. You're right. I'm not saying you're wrong. This was one of the properties. Each individual one has to be between 0 and 1. So sometimes they'll give you one and it'll have a negative probability in it. In that case, it's just not a probability distribution. But these two, or if you want to say 3 things, have to happen.
So are you saying it can either be 0 or 1? Or are you saying it can only be 1?
an individual probability, just one of the single can be 0 or 1.
Okay.
Now, if one of the probabilities is 1, then all the rest of them have to be 0 because it
Mhm.
has to add up. But Jalen, I think for the question what you said, and for this specific question, you're exactly right. Since they're asking for a missing value, we really are just looking at having them add up to 1. So I think what you said is actually for this question that you're exactly right. Not partially right. Another one like this might require a calculator because now we have decimals. All right, any guesses? You can use just what Jalen said.
Um,
I guess we add these up, right?
yeah, when I add them up, I got 0.99.
All right.
So So it would be the first one.
There you go. So here's how we did it. Lexi said add up the ones we're given. And she got this. And then we just take our little calculator and subtract that from 1. And that must be the missing one. Very good. A little repetitive, I know, but I think this is the last one of these. A little easier to add.
I got the second one.
All right. So when you added all these up, you got what?
I got 0.8.
All right. And then we subtracted that from 1 because we know they all have to add up to 1. And looks like we get the same answer you did. Good job, Lex. That might be the last one of those. And I think I want to show you one more thing here. Oh, here's one you can do. This is kind of an incomplete probability distribution, and that is a frequency distribution. What we started off with started off the class with. And so what it's missing are the probabilities. You know, if these are the X's, then what you need to put in are the probability of each one of them occurring. And then, so we need to do that first. That's just absolutely horrible looking, isn't it? I'm going to redraw it into something that's while you're working. So find the probability of a household having 0 cars. And then find the probability of a household having 1 car, so on, all the way through. A little tedious, I know, but math can be tedious. So what do we have? 5 outcomes. Should have left myself. Oh no, that's right. So I'm just rewriting it so it looks more like a probability distribution. Here are my X values. I could have 0 cars, 1 car, 2 car, 3 cars, or 4 cars. So I need you to find the probability of each one of those. Now, I would like you to leave it in fraction form, if you would, and we'll just work with them in fractions and then turn it to a decimal at the end. So the way we found, and I think it was Jalen or Mallory, somebody at the beginning, when we were finding the probabilities for these things, the very first example, how we did that when I was just had grades, number of students and the grades they got. These numbers are a little bigger, but we work it the same way. So see if you can fill in those 5 numbers, and then we'll answer the question from there.
So to find it, I would just have to count up all like the numbers like 125, 428, and so on, and then divide it. Like, so to find the probability of 0, wouldn't I divide 1000 over 125? Just to make sure I don't do it wrong.
You have it upside down, but I think you were thinking right. You would divide 125 by 1,000. So
Oh, oops, that's what I meant. Sorry.
Yeah. So add up this column. They actually gave it to us right here. But if we added up the frequency column, we'd say, okay, we got 1,000 people in this survey. So the probability of 0 is 125.
Over 1,000.
Yeah, because of that. That makes it easy.
Okay.
All right, what's the next one here?
Hold on, I just did it. 0.428.
All right, I'm just going to write it as a fraction.
Oh, sorry.
This doesn't matter. You're right. I'm not saying you're wrong. Write it as a fraction. Because I think I'm going to have some adding to do. How about for two cars?
It would be 256 over 1,000.
For 3 cars?
108 over 1,000.
All righty. And finally for 4 cars.
83 over 1,000.
There we go. And if you add all those up, what do you get? You already know what you get, don't you? You'll get 1,000.
Yeah, you'll get 1,000.
Yeah, so you get 1. So that's a legit probability distribution. Now let's answer the question. A household that has less than 2 cars. So you have to take those words and determine mathematically what they're asking. Which of these values in this column are less than 2? Now, when we say less than 2 in math, does that include 2?
No.
Yeah, 2 is not less than 2, is it?
No, it would just be the 0 and the 1.
Right. So now we actually have 2 things we have to consider. So what's the probability that a household has either 0 cars or 1 car? Because 0 and 1 are less than 2.
It's 0.553.
And we get that by adding these up. And then their answers are in decimal form. So that is exactly correct. Okay. Fortunately, I left my distribution up here because this has the same data.
Oh, wow. Easy for
Yeah.
us.
Lucky for a change, right?
Yeah.
So now all you have to do, take a minute and at least one car. What does this mean? At least one.
It would be all of them, including 0.
Is
Right.
0 at least one?
No. I mean, all of them, but not 0. I meant not 0.
Right. Yeah, very good. Because 1 is at least one.
Yeah,
That's
sorry.
the
I didn't mean to say including 0.
That's okay. Usually people get hung up on the 1 and they don't know whether or not to include the 1. But 1 in math speak, 1 is at least one.
Yeah.
So if you have one car in your household, you can say, well, I at least have one car.
Yeah.
I have one car. So like Lexi said, this is going to be all of these. What does that add up to?
875.
Very good, Jalen. 875, if you add up those 4, which are in our probability distribution here, you would get 875 over 1,000. So assuming we're using this data now, using this probability distribution, the probability of someone having a household having at least one car is 0.875. Very good.
Oh, wait, can you go back? I was gonna
Yes.
take a picture of it.
And we only got one more after that. Let me get it lined up here.
Thank you. Got it.
There you go. Now it's lined up.
Got it. Thank you.
Okay. Uh-huh. All right, one more. And that'll be it for today, and same data again. So that's good. Now, here's some between one and 3 cars inclusive. If we just said between 1 and 3, what would that mean? What numbers are between 1 and 3?
2.
Yeah, exactly, just 2. But when we say between 1 and 3 inclusive, what are we saying?
1
Yeah.
and 3.
Yeah, only.
Yeah. 1, 2, and 3. We're including the 1 and the 3. I know it's a little awkward. The language is a little awkward But that's what they're very specific, of course, in math. So if they want you to include the endpoints, they're going to tell you to include the endpoints. All right, what would this one be?
The second one.
All right, so between 1 and 3 inclusive, we would be looking at those, wouldn't we?
Yes.
You add those up and you get 0.792.
Yes.
Very good. All right, very good. So that's a little short introduction to just the generic discrete probability distribution, which is just a little bit of a extension of the frequency distributions we did a while ago. Next class, we'll look at some more advanced counting techniques. We did a little bit of counting techniques, like how many different possibilities of combinations of children you can have and things like that. We're going to look at some more complex ones that'll help you count even more complex things. Fortunately, there's formulas for it. The formula is a little yucky looking, but the calculator knocks it out pretty good. But I want you to see the formula so that if you see it later on, it won't look so intimidating. They'll say, oh yeah, that's that messy counting formula. I know how to work with that. So you don't have to memorize the formula or anything like that, but I just want to demystify it because it becomes part of what we're going to end up with, which is the binomial probability distribution. Now, because it's called the binomial probability distribution, how many outcomes do you think there are? Since it's called, yeah, because it's called binomial. Good job, Mallory. So there's a lot of things, a lot of probability distributions that fit that type. Yes, no, true, false, things like that. So that's why we usually pick that one out and do more work with it. But we'll do a little prep work before we get into it. But ultimately, we'll use an online calculator because the formula for binomial probability calculation is really, really tedious. I mean, it's just arithmetic, but you can be doing arithmetic forever. So we'll end up doing some calculator work on that, so it won't be so time consuming. But anyway, I appreciate you all coming today. I appreciate you all letting me slide for Monday. And
Yeah.
I'm feeling better today than I did Monday, so I hope I'm back
I'm
on.
glad.
Thank you. And I will see you guys. Have a nice weekend, and I will see you guys on Monday.
Have
You
a nice
too.
weekend. I'm
Thank
glad
you.
you're feeling better.
Thank you very much.
You're welcome.
Bye,
Keep us
everybody.
updated.
I will.